Hi everybody! So in today's video, which is the second video of Chapter 8, we are going to be going back to and reviewing one of the ideas that we practiced earlier this year, which is the idea of particle motion. So as a review, particle motion is talking about connecting position, velocity, and acceleration functions, and in this unit, we're going to focus on building those connections using integrals. So let's start by reviewing our learning target for this unit. I can determine values for positions and rates of change using definite integrals in problems involving particle motion, so an object that's moving. All right, let's start with this. Particle motion, as a big idea, are problems that deal with objects moving along a straight line. In these problems, you will usually be given the velocity function for the particle that is in motion. In these notes, we will focus on how to find information about the motion of the particle using the velocity function, the velocity graph, or a table of velocity values. So there are three different example problems here, one of which is all about the velocity function, one is about the graph, and one is about a table of values. Let's start with some review. So one of the things we learned earlier this year is we can tell which direction an object is moving in by looking at the velocity. When your velocity is greater than or equal to 0, we say that our object is moving to the right. When your velocity is less than or equal to 0, we say that our object is moving to the left. And when our velocity is actually equal to 0, we say that the object is stopped. Now we use, and as a big idea here, we use the sign of velocity to make these decisions. So is velocity positive, is velocity negative, or is velocity 0? One of the types of velocity that we've learned how to find throughout this year is what's called the instantaneous velocity. Instantaneous velocity means the velocity at a single moment in time. A single point. In order to figure this out, we said you use the velocity function, which is just v of t, and you plug in your value. We've also learned how to find the speed of an object. We said that speed is basically how fast you're going, but we don't care about the direction. So we said that speed was the absolute value of velocity. Earlier this year, we talked about average acceleration. So average acceleration means regular old slope. Of velocity. So to find the average acceleration of an object, we would take v at your end time minus v at your beginning time all over b minus a. It's just regular old slope. Y2 minus y1 over x2 minus x1. And we said this is different than instantaneous acceleration because instantaneous means derivative. So to find the instantaneous acceleration, we would actually take the derivative of velocity and plug in our value. Finally, one of the things we talked about earlier this year was the idea of speed increasing or decreasing. We said this is sometimes called speeding up or slowing down. In order to figure this out, we said you need to compare the signs of velocity and acceleration. If they have the same sign, in other words, if both are positive or both are negative, we are going to be increasing our speed. And if they have opposite signs, in other words, one is positive and one is negative, opposite signs, then we're going to say our speed is decreasing. Now, this is a review. It's been a while since we talked about it, but hopefully as we practice it some more, it'll come back to you because it is something we practiced quite a bit earlier this year. However, the four new questions, the four main questions that we're going to be asked now that we know how to find an integral are the following. Suppose that we know we have a velocity function and we have an initial position. If I were to ask you to find the displacement, I would do the integral from my beginning to my ending time of velocity. Now, we've talked about this before. When we were interpreting the meaning of an integral, we said if you integrate velocity, you get displacement. Now, I'm going to be asking you to find displacement, and you're going to have to do that by integrating velocity. Now, as a reminder, displacement just means how far away are you from where you started. So, suppose you take 5 steps to the right and 3 steps to the left, your displacement would be 2. Because when you stop, you're going to be 2 steps away from where you started. Now, a separate idea is the idea of total distance traveled. And here's how total distance traveled is different. If I take the same situation, 5 steps to the right and 3 steps to the left, and I ask for the total distance that you traveled, you would say 8. Because now we want this 3 to count as positive steps. Whereas here, the 3 counted as negative steps. You went backwards. So for total distance traveled, the direction doesn't matter. We want to just make everything positive and count it all. In order to do that, we're going to integrate the absolute value of our velocity function. Now, the reason we use the absolute value here is because doing the absolute value forces all of our distances to be positive before we add them up. You will also notice that the absolute value is inside of the integral around the velocity function. It's not around the whole outside of the integral, it's inside. One of the other questions we're going to be asked is about the idea of actual position. So this is the same thing as asking, where are you now? In order to figure this out, we use our starting position plus the integral of velocity, because that tells us how far away are we from where I started. So where did you start plus how far away are you now? And that'll tell us where we're actually standing. Now, one important note is that the beginning of this integral, the a, is always the time of the initial position, which is not necessarily always 0. For example, I might know that when t was 0, my position was 10, but I might also know that when t was 5, my position was 10. Regardless, whatever the t value is, whatever the starting time is for your initial position is what goes here. Last but not least, we have average velocity. Now, average velocity would be like average value. If you've got velocity and you want to know the average, you've got to add them all up and then divide by however many you added. So we would use the idea from the previous section to find the average value. Let's go ahead and look at some example problems where we're asked to use these ideas. So, the first example problem that we're going to be looking at has to do with using a table of value, a graph. In this graph, we are shown the velocity of a particle that is moving along the x-axis over the interval from 0 to 8. The velocity is moving in inches per second. For part A, it says, for what intervals is the particle moving to the right? Moving to the right means has a positive velocity. So moving to the right means we're looking for where velocity is positive. On this graph, that would be the sections of the graph that are above the x-axis, because those would be the places where my velocity values are positive. So I would say that my intervals are from 0 to 3 and from 7 to 8. And to justify my answer, I would say because the velocity is greater than or equal to 0. For problem B, it says, for what intervals is the particle slowing down? Now, there are 2 different ways to be slowing down. We can have a positive velocity and a negative acceleration. We can have a positive acceleration and a negative velocity. When we learned about this back during first semester, we said there were 2 things to look for. we could be uphill, so going uphill, and below, which means positive acceleration and negative velocity, or we can be downhill and above, which means negative acceleration and positive velocity. So kind of opposites. Uphill would be like a positive slope, but below, and then downhill would be like a negative slope, but above. So there are a couple different places on the graph where this happens. Uphill and below would be this section of the graph right here, and downhill and above would be this section of the graph right here. So my object or particle is going to be slowing down from 2 to 3 and from 6 to 7. You'll notice again, as a reminder, whenever acceleration gets involved, we use open parentheses. Whenever it's just velocity, we use closed. And we would say because my velocity and my acceleration have opposite signs. Next, we're going to be looking at where the particle changes directions. So changes directions means velocity changes from positive to negative or from negative to positive. Now that's going to happen at places where the graph switches from above to below or below to above. So in this graph, it would be here and it would be here. I would say my particle changes directions at t equals 3 and t equals 7 because v of t changes signs. Now that's kind of a review. All three of those questions are things that we've talked about before earlier this year. The next question is one of our new ideas. The next question says, suppose the particle's position at t equals 0 is 9. So what they're doing here is they're giving me an initial value. When t is 0, I know the position. What is the new position of the particle at t equals 8? So they're asking me to find the new position. In order to find a position, I need to start with my initial position, which in this case is 9, plus the integral from my starting time, which in this case is 0, to my ending time, which in this case is 8, of my velocity function. Now, in order to figure this out, I'm going to go back to the idea that an integral is just an area. So I'm going to have 9 plus, and here's where I'm going to calculate some areas. This first area right here on the graph is just a trapezoid. So I would have 1/2 times the height, which is 3, times base 1, which is 3, plus base 2. Then the second area is a trapezoid, but it's below. So instead of a plus, I would have a minus 1/2 times the height, which is 3, times base 1, which is 4, plus base 2, which is 2. And last but not least, I have this third area over here, which is a triangle. So I would have 1/2 times the base, which is 1, times the height, which is 3. Now I'm going to simplify this. So I have 9 plus 3 plus 1 is 4, over 2 is 2, times 3 is 6. 4 plus 2 is 6, over 2 is 3, times 3 is 9, and 3 over 2. Now this 9 minus 9 cancels, so I just have 6 plus 3 over 2, which is either 7.5 or 15 over 2, depending on what you would like to write it as a fraction or as a decimal. The next question says, what is the total distance traveled? Now, this is a little bit of a different question. Total distance traveled, we said, was the integral from 0 to 8 of the absolute value of v of t. Now, you'll notice that in every single question, I'm setting up my integral before I do my evaluations. And that's because on the AP test, that will oftentimes earn you partial credit. So the absolute value means that when I add up all of these areas, just like I did in the previous problem, I'm not going to count this area as a negative. I'm actually going to count this area as a positive because I'm absolute valuing, so I'm adding it up. The first area is still going to be worth 6, which I got from right here. Instead of doing -9, I'm going to do +9. Even though that area is below, I want to count it as a positive. Plus 3 over 2, which means I get 16.5, or we could write that as 33 over 2. Last but not least, the problem here at the bottom says what is the displacement of the particle. Now, displacement would just be the integral, the regular old integral of velocity. So this time, instead of forcing this area to be positive by doing the absolute value, I'm just going to leave it I'm going to leave it negative. So I would have 6 minus 9 plus 3 over 2, which means I have -3 plus 3 over 2, which is -1.5 or -3 over 2, depending on which way you want to write it. Either way is totally fine. All right, that is an example of what one of these problems with a graph might look like. Now let's take a look at a problem with a table. So in this problem, it says Johanna jogs along a straight path for between 0 and 40. Johanna's velocity is given by a differentiable function v. Selected values of v, where t is measured in minutes and v is measured in meters per minute, are given in the table below. Use the data in the table to estimate the value of v prime of 16. So if I want to find v prime of 16, then I need to take the derivative. However, I can't take the derivative here because I don't have an equation. So to estimate this, I'm going to use the slope of the two closest numbers available. In this table, the number 16 would fall between the numbers 12 and 20. So I can say that the derivative at 16 can be estimated by just doing regular old slope between the two closest points possible. To do this, I would just do 240, so y2, minus y1, which is 200, over x2, which is 20 minus 12. That means I get 40 over 8, which is just 5. Now, it does not say here in the instructions that I need to give units. And on the AP test, it's always a good rule of thumb that you don't put down any extra information, because if you do extra work and it happens to be wrong, it will count against you. Whereas you didn't really even have to do that work in the first place. So it wouldn't have counted against you to just not write it at all. Part B says using correct units. So now you're going to notice that we have using correct units. Explain the meaning of the integral from 0 to 40 of the absolute value of v of t in the context of the problem. That's part 1 of this question. Part 2 of this question is to approximate the value of that same integral using a Riemann sum with 4 subintervals. Reading the directions here is going to be really important because the directions give you a clue about what you're supposed to do. And these directions are telling me that there are 2 parts to these answers. The first part is to explain the meaning. Now, as soon as I see that I'm supposed to explain this meaning, I'm going to copy that down. The integral from 0 to 40 of the absolute value of v of t, and I would say means or represents. Now, going back to what we learned on the first page of our notes, if we integrate the absolute value of velocity, we are finding the total distance traveled. So I need to use that as my noun. Don't forget, we need noun, units, time. Represents the total distance traveled, so that's my noun. Total distance traveled. Distance traveled by Joanna. So noun, units measured in And we're going to measure our distance in meters. So when we integrate, we're going to be getting just meters because meters per minute times minutes would just be meters. Measured in meters. Then we need our time. Now our time is going to be from 0 to 40. So from t equals 0 to t equals 40 minutes. That is part 1 of our answer, and it is very important that you separate and highlight that you answered both parts of this question in your mind and on your paper. So there's part 1. I explained what it means. Part 2 now is to actually do these computations using a right Riemann sum with 4 subintervals. So I'm going to set this up by making 1, 2, 3, 4 spaces. It's how I organize my work. My x values are 0 to 12, 12 to 20, 20 to 24, and 24 to 40. My y values, I'm going to use the right side of each interval, are going to be 200, 240. Now, remember, it's the absolute value. So even though this says negative 220, I'm just going to make it positive 220 and 150, which means what I really need to add up right now is 12 times 200 plus 8 times 240 plus 4 times 220 plus 16 times 150. Now I have a calculator to help me with this. Thank goodness, this is a calculator question. So I would say 12 times 200 plus 8 times 240 plus 4 times 220 plus 16 times 150. And that's going to give me 7,600 meters. So I'm going to say the integral from 0 to 40 of the absolute value of v of t dt equals 7,600 meters. And I'm going to put a box around that because that's the answer for the second part of the question. For part C here, it says Bob is riding his bicycle on the same path. Between 0 and 10, Bob's velocity is measured by b of t. Now, I always like to, whenever I'm given a new equation in a problem, I like to highlight it and label what it is. This is Bob's velocity, where b of t is measured in meters per minute. Find Bob's acceleration. So in order to find acceleration, we need the derivative of velocity. So I would say the acceleration would be b prime of 5. Now again, I have a calculator, so I'm going to go ahead and just use that. So I'm going to go to math option 8, which says take the derivative. I'm going to type in my function, which is x to the third power minus 6x squared plus 300 at 5, and I get 15. Now, it does not say that I need units here, so I'm not going to put units because if I do extra, then I could be marked down if I do it wrong. The units would be meters per minute squared. Part D says, based on the model from Part C, find Bob's average velocity. Now, average velocity means we need to add all these things up and divide. So I would do 1 over 10 minus 0 times the integral from 0 to 10 of b of t dt. Now you'll notice I'm writing down what I plan to do. I'm not just writing down a number as my answer. It is very important to show your work. So on my calculator, I'm going to do 1 over 10 times math option 9, which is the integral from 0 to 10 of x cubed minus 6x squared plus 300 dx, and that gives me 350. All right, we're going to go ahead and save the last problem for a warm-up in class tomorrow. Thank you guys so much for watching and have a great afternoon.